Today, lesson 6C, Dilations and Similarity. This is the first of 3 days that we'll be spending on this topic. We just had a quiz last week on congruence, or through congruence, I should say. And congruence always came from the transformations, translations, rotations, and reflections, and we term those as rigid motion. Today, we go into something that I kind of started in the last lesson, which is this idea of dilations. All right, so far in our study of transformations, which the types of transformations we've talked about, we've termed as rigid motion. We've come to the realization that any translation, reflection, or rotation, or any combination of them, preserves congruence. Recall, congruent shapes have the same exact size and shape. Also, congruence means that all corresponding sides are congruent, and I've been making you prove that quite a bit, and that all corresponding angles are congruent, and we'll get to the corresponding angle part next week. But what if we're not interested in using just congruent shapes? What if we want shapes that are reduced or enlarged versions of our original? And this is where dilations come in, and this is where you'll need to start filling in some things in your notes. A dilation is a transformation in which a shape is enlarged or reduced by a given factor around a given center point. Since the shape is changing size, it is not rigid motion. This means that congruence is not preserved. In addition, dilations lead to similarity or similar figures. And in just a minute, we're going to do some review or some background knowledge from 7th grade that deals with this idea of similar figures. And I'm going to go through that very quickly because it is review from 7th grade, but we need to quickly review that before we can get into what we're about to talk about today. The two figures are similar if one is a dilation of the other. And you may have heard the term pupil dilation before. If you've ever been to an optometrist, that's one of the things that they will do right before they test your eyes, and that's where your pupil expands, gets smaller, expands, gets smaller. And that's really the idea of what we're doing with different shapes. All right, similar figures. This is a slide from 7th grade, no matter what class you were in. Figures that have the same shape but not the same size. In other words, one is an enlarged or reduced version of the other, and I kind of just mentioned that when we're talking about or defining dilations. So here we have a rectangle that is 100 by 50, and here I have an enlarged version of that is 200 by 100. In other words, the rectangle on the right is clearly bigger than the one on the left. In fact, the sides are twice as big. And the other way to look at that is the left-hand rectangle, the sides are half as big as the ones on the right. And what that leads us to is an idea called the scale factor. And the scale factor is the ratio of any two corresponding lengths in two similar figures. Now, in this example, it's clear to see that the sides on the rectangle on the right are twice as big. But sometimes it's not clear, depending on what the numbers are. And this is where you would want to compare those ratios. So for example, if the numbers weren't as clear as they are here, we can compare the sides of the small rectangle to the sides of the large rectangle. So notice, first of all, that 100, the side of 100 lines up with the side of 200. We could check that ratio, or we could check this ratio right here. Both of them tell us what that scale factor is. In other words, the rectangle on the left, the sides are half as big as the rectangle on the, I don't know whether I said left or right, but the left sides of the rectangle length on the left are half as big as they are on the right, if I didn't say that, because we have an enlargement here. So here's another slide back from 7th grade. I have some questions for you. How many times bigger are the sides of the second rectangle than the sides of the first rectangle? What are they? Just say it. 3 times bigger. All right. I have another question for you. What is the scale factor? Anybody know what that would be? 3 to 1. Okay. because, once again, the sides of the rectangle on the right are 3 times bigger than the one on the left. Here's another question for you, and you might have to figure this out if you don't know this from last year. What is the ratio of the perimeters? And if you don't know that, figure it out very quickly. Anybody know what that would be?
3 to 1.
It's 3 to 1. The rectangle on the left has a perimeter of 10. The rectangle on the right has a perimeter of 30. As it turns out, if the scale factor is 3 to 1, the perimeter is also 3 to 1. And so that leads us to the fact that the scale factor has the same effect on the perimeter as it does on the side lengths. Here's another question for you based on these two rectangles. What is the ratio of the areas? Now, this idea that is from the 7th grade, I'm going to come back to this idea later in this lesson. But if you don't know what that is, quickly figure it out. I'm asking you what the ratio of the areas is. So the ratio of the areas, the rectangle on the left has an area of 6, the one on the right 54. The ratio of the areas of those two would be 9 to 1. And as it turns out, and one thing you should have talked about last year, is the effect on the area is the scale factor squared. So since the scale factor was 3 to 1, the effect on the areas is that squared, or 9 to 1. So what I want you to do is I want you to quickly answer those same questions for this situation. So, how would you compare the sides of the smaller rectangle to the sides of the larger one? Raise your hand if you know. Yep. It would be 1 to 2, right, because they're half as big. So that leads us to the scale factor. Since the rectangle sides of the rectangle on the right are half as big as they are on the left, that leads us to a scale factor of 1 to 2. And there's 2 different ways of writing scale factor. We could write it with a colon or as a fraction. And so I have the same questions that I had for you last time. What's the ratio of the perimeters? It's what? 1 to 2. What's the ratio of the areas? It's 1 to 4. And so if you didn't remember that from last year, you might want to jot down a few of those ideas, because we are going to come back to that idea of the ratio of the perimeters and the ratio of the areas later on in this lesson. One of the other things from 7th grade that leads to dilations is this idea right here. And we talked about this actually earlier this year, where we verified slope by using similar triangles. This is a slide from earlier this year. We had a ratio of 3 to 1, rise 3, run 1. Then we found another similar triangle there. That had a rise of 6 and a run of 2, so that's a ratio of 6 to 2, which simplifies still to 3 to 1. And then we had a bigger one right here. And all of these verified that the ratios were the same for all of those similar triangles. So another example of things that we've done in the past. And then here is a slide from last year. I'm telling you that those 2 rectangles are similar. Anybody know what this side would have to be right here to maintain that similarity? What would it have to be, Emily? It would have to be what? 8? Isn't that right? Isn't it 8? So the question might be, well, all right, well, that one's nice and easy, but how would you do that if that 6 was a 5, for example? Well, this is where the idea last year, where proportions came in, where we could set up a proportion dealing with like the ratios of the small rectangle to the large rectangle. So watch how I set this up. X over 24 equals 6 over 18, and then we could solve that proportion by cross-multiplying. That's kind of the way that we dealt with these this year. And then divide both sides by 18, and we would get x equals 8. So that tells us that this missing side here has to be 8. Now, last year you may have solved it a slightly different way, but it doesn't matter. You're still going to get 8. All right, so I know this next problem is a background knowledge problem, but I do want you to go ahead and somewhere where there's a blank spot in your notes, go ahead and quickly find that missing side. This is where the idea of proportions comes from. And I know there's several different ways of setting up a proportion. I'm going to go with 12 over 10 equals 8 over x. And then we could cross multiply one way and get 12x. Cross multiply the other way, get 80, divide both sides by 12. And there are other ways of solving for x there, but regardless of the method that you use, you should get 6 2/3 for that missing side there. Okay? So we're going to keep coming back to some of those ideas from 7th grade. But let's go to the very beginnings of dilations and how things work with dilations. So here we have a problem. You have this graph and you have this word problem, so let me quickly read it. It goes something like this. Computer animators are working on designing the head of a dragon for a new video game. The picture below shows the original shape and size of the dragon's head. However, when the dragon eats a plant, it doubles in size. If the dragon eats a cricket, the dragon triples in size. When the dragon enters a cave, the dragon shrinks to half its size. And so there are 4 animators who have submitted proposals for how to double the size of the dragon's head when it eats a plant. And you can see that all to the right in a rectangle in your notes. And it looks like this. Animator 1 submitted that rule. Animator 2 applied the rule right below that. And Animator 3 and Animator 4 and Animator... there's 4 of them. 1, 2, 3, and 4. So what you need to do is you have a table right below that, and you have some ordered pairs that are in your table. 2, 2, 6, 8, 8, 8, and so on. And so you want to apply each of these rules, and here's what I would do if I were you. I would do Animator 1 first. So do the 2x, y for the rule. Find all those new ordered pairs, plot them, use your ruler to connect them as you go, and the dragon's head is going to change slightly. Then go through and do Animator 2, which follows the rule x, 2y, and so on. So what you're going to have is you're going to have the original dragon head, and then you're going to have 4 others right on top of that, and then we're going to answer some questions from that. So I'm going to give you about 4 to 5 minutes to deal with this, and I do want you to compare. As you finish one dragon head, I want you to compare with your shoulder partner. So some of you are filling out the entire table right now. That's fine. But just after you graph the first dragon head, the new one, from Animator 1, compare with your shoulder partner, then do the second one, then the third one, and then the fourth one. And once again, I'll get back with you in about 4 to 5 minutes. All right, so we were supposed to graph all 4 of these rules on a coordinate plane. And so let's first of all check your table. So here were the ordered pairs of the original dragon. And then the first animator went by the rule 2x, y. So that changes all of the ordered pairs to that. The x coordinate, or the first coordinate, is double, whereas the y coordinates stay the same. Animator number 2, the x values, or x coordinates, stay the same, and the y values are doubled, or multiplied by 2. The third animator has added 2 to each of the x coordinates and y coordinates, so both of them changed. And then the fourth animator doubled each of the x and y coordinates. So when we plot those, this should look something like this. Here is the original. There's Animator 1. Should look like that. Let me take that away. Here's what Animator 2 should look like. We'll take that away. Here's what Animator 3 should look like. We'll take that away. Here is what Animator 4 should look like. All right, so now we have a couple of questions that I want you to answer with your shoulder partner. That would be question number 2, and then question number 3, all 3 parts. So I'll give you a couple of minutes to answer both number 2 and number 3, all parts, with your shoulder partner. Go ahead. Number 2, it says, which animator's rules results in a dragon size that is the same shape as the original dragon, but twice the size? I was walking around looking, and most of you realized that that was the fourth animator, which was the rule 2x, 2y, because we're basically doubling each of those coordinate values. What is the same about this dragon compared to the original dragon, and what is different? Well, what's the same is it's the same shape, but what's different is it's a different size. It's a enlarged version of that. Number 3, describe what the coordinate rules of the other 3 animators do to the dragon's head. I was walking around looking at different things. What some of you said for this animator, which is animator 1, is that it made the head wider. Well, that's kind of what I'm saying right here, just in more words. Stretching it out in the horizontal direction. What some of you said for the second animator is that it made the head taller. Well, that means it's stretching it in the vertical direction. Same idea. And for the third animator, did the head size change? No, because that's x plus 2 comma y plus 2. That's a translation. We moved it basically 2 to the right and 2 up. So it's congruent because we just translated. Translations, rotations, and reflections lead to congruent figures. All right, so now let's go to number 4. In number 4, it says the animators need your help coming up with the coordinate rule that would reduce the size of the dragon's head to half the size when it enters the cave. So you need to come up with a coordinate rule. Put that coordinate rule right here. And then write the coordinates for your new rule, and then graph those coordinates to prove that the head is half the size of the original one. So I'll give you a couple of minutes to do number 4. The graph for number 4 is actually below it, but all the way to the left. So do parts A, B, C, and D. All right, so number 4, we were supposed to create one that was half the size. So that would make the coordinate rule 1/2 x, comma 1/2 y. I think that's obvious. There would be the image ordered pairs that we would use based on the pre-image. And when we graph that, it should look like that right there. So some things that we will need to notice about that, and they're based on some questions that I'm about to ask. First of all, what's the same about this dragon compared to the original? Well, it's the same shape. What's different? Well, it's smaller. It's a reduced size. So what about the slopes of the corresponding sides? Well, when you are doing a dilation, the slopes of the corresponding sides are the same. And you can clearly see that right there if you were to check all of the corresponding sides. Also, the corresponding sides are parallel to each other. And I think you can clearly see that as well. Just for example, that side right there, and that side, this side, and this side, and so on. The corresponding sides are parallel. The corresponding angles are congruent. So what I mean by that is, for example, that angle right there and that angle right there. All the corresponding angles are congruent to each other. Not only that, but since we have a scale factor of 1 to 2, the perimeters, how would they compare? Well, the perimeter would be half as big on the red dragon head compared to the black one. And as far as the areas go, whatever the area of the black one is, the red one would be 1/4 as big as that. Just utilizing some ideas that we talked about earlier in the lesson. Now, part E. You don't have to graph this one, and some of you already did this question. Write the coordinate rule that would triple the size of the dragon's head when it eats a cricket. If you didn't already do that, I will give you 30 seconds to come up with that coordinate rule, and that's about 25 seconds too long. Tatiana, what's that rule? 3x, comma 3y. Very good. All right. So what conclusions can we come to? Well, it would be 3 times the size of it would be 3 times bigger as far as the side lengths. But the same things happen in this one that happened in the last one. The slopes of the corresponding sides are the same. The corresponding sides are parallel. The corresponding angles are congruent. The perimeter of the new one would be 3 times as big, whereas the area would be 3 squared or 9 times as big. And the scale factor would be, of course, 3 to 1. All right, a little summary of dilations, of the beginnings of it today, and you have a few blank areas that you need to fill in. The properties that are preserved under a dilation: corresponding angle measures are congruent, parallel lines remain parallel, Some of these things, we saw that when we were talking about congruent shapes. The slopes of the corresponding sides are the same. Corresponding side length, however, is not preserved unless the scale factor is 1. The ratios of the corresponding sides are equivalent, and that leads to the scale factor. And then the last part, dilations create similar figures. And that is it for today.